Okay, hello everyone and welcome back to your YouTube channel and welcome to this very amazing video today. I have a practical video with a numerical example where you will learn how to calculate the accelerating torque in a synchronous machine. And without further delay, let me start here. Consider a 60 Hz 4-pole synchronous generator. The apparent power that you can find in the nameplate is 85 MVA. The nominal voltage, stator voltage, is 13.2 kilovolts. This is RMS line-to-line voltage, okay? And this machine has a rotational inertia H of 6.42 megajoules per MVA, okay? Now, initially, this generator is delivering the rate apparent power in MVA at power factor 0.8 lagging. However, suddenly a fault occurred, and this fault reduced the electrical power by 40%. Now, the big question here is, as we have a reduction in the electrical power, this machine will keep the mechanical power as it, and will have some acceleration. Sorry. Now the question is, what is the acceleration torque? In this case, in the MKS unit system, Newton meters, and we can neglect in this case losses, and we can assume constant the mechanical power at the shaft during the acceleration process, okay? We want to express the result, the acceleration torque, in Newton per meters. Well, we are using this amazing live script, Matlab live script. First step, we clear all the variables. Then we define some parameters here, the input data, frequency 60 Hz, rate apparent power 85 MVA, 4 poles, rotational inertia 6.42 megawatt second per MVA or megajoules per MVA, and the operating power factor here is 0.8, and it is a lagging power factor. Now the job here, first step. We want to know what is the nominal situation before the fault. In other words, we want the electrical power before anything happens. And to calculate that, we multiply the apparent power, the nominal apparent power, by the power factor. In this case, it's very simple. Put the number together, 85 MVA multiplied by the power factor, 0.8. And we obtain that the magical number is 68 megawatts. That means that initially the machine is working in a steady state. The acceleration is 0 because the mechanical and the electrical power, they are the same, 68 megawatts. However, during the fault process, during the fault situation, the electrical power output of this synchronous machine is reduced by 40%. And 40% of 68 megawatts is basically 27.2 megawatts. And that difference, that 40% reduction, to be honest, is a reduction in the electrical power, and that is creating now the situation where mechanical power is larger than electrical power and the machine is accelerating. What I'm trying to tell you is that basically these 27.2 megawatts are increasing the rotational speed and including acceleration in the rotor. Now here I am showing some equations to calculating the electrical synchronous speed and the mechanical rotational speed, okay? I showed this equation before, and all of you are familiar. If not, please go to my previous video and you will be able to see the equations. What I want to show you here is that the electrical synchronous speed is 3,600 RPM, and the mechanical synchronous speed is 1800 RPM. And the reason for that is because you must remember that this is a 4-pole machine, 60 Hz. Finally, we want to obtain the acceleration torque. And all my students, they are so clever that they know that there is a connection between power and torque. And the relationship between power and torque is the rotational speed. That means that here I can define the accelerating torque as the ratio between the accelerating power and the rotational speed. However, again, in this situation, I have been very careful with my students regarding the units. I need that my students understand how important the units are, because otherwise you can make very bad mistake and the numerical results can be totally wrong and also physically unfeasible. For that reason, here, what we need to do is divide, in this case, the accelerating power, 27.2 megawatts, divide by the rotational speed, but this rotational speed is in mechanical radians per second. And we are dividing in mechanical radians per second because this torque is a mechanical torque. And this mechanical torque here that we are calculating is at the shaft, and in this case, when we put the number together, we obtain this huge number. 144,300 Newton per meter. Okay? This number is huge, but this is because the units that we are using are the most basic, Newton per meter. Okay? Well, again, what is very important for all my students in this exercise, in this example, in this very plain and basic example, is that you need to care about units, okay? You need to care about units because units can make you make very bad mistake if you confuse the units. Again, please reflect and take care about units. Well, this is all for this video. It was a very short video, very practical, very fast, very simple. I hope you enjoyed the video. If yes, please subscribe to the YouTube channel and a like or leave a comment, and I will be extremely happy to help you, okay? Thank you very much for watching, and I will see you at the next one. Bye now.